the Cambrian is a pivotal period, a key element in our history. The Cambrian era, you will have understood, makes our planet take a new turn. The Cambrian marks the beginning of the primary era, but also, and especially, an explosion of underwater life. Organisms develop, they multiply, they evolve and adapt to their environment and to a new way of life. Some of them will be equipped with a skeleton, others with shells or carapaces. For these animals, it is a new way of approaching the environment and of fighting for their survival. But for us humans, it also means that we will be able to find traces of their life on Earth much later. This was not the case before. That is why it is still so difficult to determine the extent of underwater life in the Precambrian. But 540 million years ago, a new form of life developed underwater. They can finally leave shell impressions or traces of their skeletons, elements that will fossilize over time and become the first witnesses of underwater history. To discover this history and to meet your first living Cambrian organisms, I will take you to Canada. There, a 525-million-year-old rock has offered its most beautiful prehistoric treasures. When we talk about prehistoric animals, we more easily evoke the Jurassic, the cinema helping, or the Cretaceous. However, many other animals, just as fantastic and important, have marked the history of the Earth. Let's go now to Canada. We are in the Rocky Mountains of Yoho National Park, on the western slope of Mount Stephen in Canada. It was here in 1909 that Charles Doolittle Walcott, a British paleontologist, made an absolutely incredible discovery. There was such a large pool of fossilized marine animals that it was given a name: the Burgess Sea Trough. The quantity is important, nearly 65,000 fossil specimens in all, belonging to 120 different species. But the quality is also just as spectacular. The majority of the fossils are a bit damaged. It is rare to have a whole skeleton perfectly preserved. Time has done its work, and geological and climatic changes have inevitably had an impact on the remains of the past. Yet in the Burgess fauna, time seems to have stood still. The footprints are remarkable because the soft parts of the animal in question can also be seen, which is very rare. The phenomenon is explained by a slow decomposition of the animals. The shales in which the fossils were found were not formed gradually, but through a series of brutal and intense mudslides. The soft parts were isolated from the oxygen in the water, which slowed down the decomposition of the bodies. Fast burial and slow decomposition is the winning combo for preserving fossils over millions of years. Now that you've learned about these early fossils, let's take a trip down memory lane. Are you ready to go to the Cambrian? On the geologic timescale, we are now between 359 to 299 million years old. As you can see, things look quite different. The average global temperature is 25 degrees Celsius or 77 degrees Fahrenheit. If this kind of climate seems mild, there is no life on the ground. Look at the continents. All is rock, emptiness, and solitude, as far as the eye can see. This is easily explained. At this time in our history, the ozone layer is so thin that it does not protect the planet from the sun's ultraviolet rays. The slightest hope of life that could have shown up on the surface would have died, victim of our solar star. The waters are relatively warm, and the atmosphere contains a little oxygen, and very little CO2. In spite of rather difficult conditions, they have nevertheless allowed life to proliferate. This is still impossible on the continent, but the ocean is full of all kinds of marine specimens. The first fossiliferous animals, i.e. capable of leaving fossil traces, arrived in the ocean. Who would have thought that the invention of the shell and the carapace would be so significant? Invertebrates are king and populate most of the warm and shallow seas. The first green algae develop, as you can see. They are unicellular or multicellular algae. They were limited to the shores and lines of the coasts where they formed a short carpet, like our modern bryophytes. These algae serve as a food base for a large number of species. Nature set up the first food chains with primary consumers, vegetarians, and secondary consumers, carnivores and predators. Let's go deep into the warm waters of the Cambrian to discover these seabeds. You can see worms, sponges, mollusks, and echinoderms. These major groups of animal classification are still present today, but there are groups that did not survive and ended up disappearing. These are the ones we will see first. Let's start with the trilobite. The trilobites owe their name to the shape of their body. They are made up of a median lobe and 2 lateral lobes. They live near the seabed. They are not easy to see in these funds. Here is a small specimen, 5 centimeters or 2 inches approximately. It is a Cotycops fernandini. Some members of the trilobite group are much smaller, only 1 millimeter. Other large specimens can reach 70 centimeters or 28 inches. This Cotycops fernandini seems quite fragile in this complex and primitive environment. It is, however, perfectly adapted to its environment. Its eyes are equipped with many facets which enable it to see 360 degrees. Impressive, no? This faculty undoubtedly allowed him to facilitate his research, to feed himself more easily. It could probably have survived despite the mass extinction that occurred at the end of the Permian, the last phase of the Paleozoic, in the salty waters of the ocean. Unfortunately for it, it did not venture into fresh water, and therefore did not survive. Here is another member of the arthropod group. It is the Yohoia tenuis. It is very small, between 7 and 23 millimeters only, so it is difficult to see. But if you get a little closer, you should be able to meet some. They were quite numerous in this part of the ocean. They occupied the sandy and muddy bottoms. This small animal has some assets to compensate for its small size, notably a cranial shield and 13 tergites. The tergites are sclerites, i.e., polycrystalline plates. They harden thanks to a process called sclerification. The tergites are sclerites which are located at a particular place of the body of the animal. We find them on the back, and they enclose its abdomen. Our specimen of Yohoia tenuis has 13 tergites. The first 10, as you can see, end in the form of a point on the sides. The last 3 form a tube, which protects this part of the body. Its tail is shaped like a paddle. To feed itself, it uses the small appendices that you see at the level of the skull. They look like small bent legs and some kind of fingers at the ends. They could thus manage to capture prey, feeding only on dead animals. Here is now the last of the group, the Canidaspis. It is not the least important because it seems to be one of the oldest crustaceans. As you can see, it moves by walking on the seafloor. It is a benthic feeder. It uses its appendages to stir up the mud and find food. Let's look at another group, the Archaeocyathra. The Archaeocyathra are the first reef-building metazoans. A reef is a chain of living organisms, like the coral reefs we know. The Archaeocyathra are not corals, however. They should not be confused. They are calcareous sponges. The sponge is made up of a calyx, a kind of porous cone, nested one inside the other to form an internal and external wall, and thus protect the organism living inside. Some specimens occupy the whole calyx. Other organisms occupy only the upper part of the calyx. There are many species in this group. These sponges feed by filtration. Zooplankton, phytoplankton, and organic particles in suspension constitute their diet. Fragile, they can only survive under very strict conditions. They cannot tolerate any change in temperature, salinity, salt content, and depth. This is undoubtedly what led the species to its loss. It is probably the first super predator of our planet. The Ediacaran is not very aesthetic and lacks a bit of charm, but to feed, it is better to be powerful, skilled, fast, or fine strategist than cute. But its eyes allow it to flush out its victims. Its mouth is a real cutthroat. It is equipped with sharp bone plates to crush its prey. Let's go back to the surface and let this Ediacaran go about its business. It perfectly symbolizes the enormous evolutionary leap of living organisms since the Cambrian. We are going to leave the Cambrian era to meet the aquatic animals of the next era, the Ordovician. The Ordovician is the second of the 6 geological systems that make up the Paleozoic. Differentiating the geological layers allows for a better understanding and appreciation of the environment in which we find ourselves. Until the 1800s, the Cambrian preceded the Silurian. Then in 1879, Charles Lapworth understood that another phase lay between the two. The global ocean and land cooled. Vast reservoirs of oil and gas appeared. There was also a new explosion of underwater biodiversity. This is why it was essential to differentiate it from the other two. On the geological timescale, the Ordovician is located between -485 to -443 million years. The Baltica and the Laurentia will collide. Towards the end of this period, Gondwana was close to the pole and largely covered by glaciers. At this point in the history of our oceans, sea levels were higher than in the Cambrian, and temperatures had risen to 30 degrees Celsius or 86 degrees Fahrenheit at the surface of the globe. The number of genera and families of living beings tripled or even quadrupled compared to the previous era. What also marks the arrival of the Ordovician is the appearance of Lapitognathus fluctivus. It belongs to the now extinct family of conodonts. This species finally resembles a species that we know today, the eel. What allows to differentiate it, they are its head and its teeth. For a long time, the only fossils found were its teeth. From then on, it was difficult to imagine the rest of its body from a simple jaw. Since then, we have some elements that have allowed us to define the soft part, and thus to estimate that it is similar to a kind of eel. Although the species has teeth, scientists think that it was mainly used as a filter to feed on plankton. After studying the body, it is unlikely that the animal is classified as a predator. Other groups, which had already appeared in the Cambrian but were still very few in number, developed during the Ordovician. This is the case of the articulated brachiopods, cephalopods, crinoids, ostracods, bryozoa, graptolites, conodonts, as we have seen previously, and of course, corals. The first ectoprocts appear at the same time. They are what we call moss animals. They are sessile and live in a fixed way on a rocky element, for example. The body of an ectoproct gathers a very large number of small animals called zooids. This is called a colony. Each zooid lives in a small lodge made of limestone. It is these lodges connected to each other that form the skeleton of the colony. The colonies can take different forms, similar to corals, to moss, or even to lace. The corals were isolated until now. They will start to develop more widely. Here you can see the first coral reefs in the ocean. As you can imagine, these reefs are home to life. You can find the first bivalves near these primitive corals. If the bivalve family already existed in the Cambrian, it evolved and developed largely in the Ordovician. The shell of a bivalve is composed of calcium carbonate and includes two parts, generally similar, shell equivalents, which are called valves. These are joined along one of their edges by a flexible ligament. A strong increase in the diversity of bivalve species is accompanied by the appearance of disodonts, heterodonts, and taxodonts. Among bivalves, we can recognize the Raffinesquina in a half circle, or the more elongated Modiolopsis. Other mollusks, such as gastropods, are developing. This class of mollusks is characterized by the torsion of their visceral mass. They have a very wide variety of forms, but can be recognized generally by their characteristic twisted, univalve dorsal shell when present. They have a foot and a distinct head. Their foot is flattened in a broad ventral sole, which makes them excellent swimmers. Their head, it comprises eyes and a radula. Here is Stepsodiscus, and a little further, Chippewela, both aquatic snails. I would now like to introduce you to another animal with a shell, but this one is much larger and known for its hunting prowess. To reach 2 meters or 6 feet long, the shell was around 10 meters or more than 30 feet. This Orthoceras is rather impressive. It was a formidable predator and quickly rose to the top of the food chain. It could be compared to an octopus or a gigantic squid. To hunt, it used its tentacles to capture its prey. Then it devoured it with its beak. Living in deep water, this animal had a very bad sight. But as for the majority of the living beings in this case, other senses compensate this handicap. With him, it is the sense of smell. He smells from far away his future victims, which become his dish of the day. We did not see much vertebrates until now. Even if mollusks are very present, vertebrates are becoming more and more important in the ocean. Here is one of them, a fish of the genus Agnathus. This means that it has no jaws, but it has no trouble feeding for all that. The mouth of Sacabambaspis genvieri was lined with nearly 60 rows of small bony mouth plates that were probably movable to provide an effective sucking action through the expansion and contraction of the oral cavity and pharynx. It looks somewhat like a tadpole with its large head, flat body, and wagging tail. A big tadpole of 25 centimeters long, that is to say, almost 10 inches. We have just started this journey, and yet events are already getting complicated on land and at sea. At the end of this period, the planet experiences the first mass extinction and the second largest ever known. between 60 and 80% of marine species will disappear. The cause? A drastic decrease in atmospheric CO2, leading to a global cooling. Indeed, one of the factors preventing ice ages in this era is the high concentration of CO2 in the atmosphere, which at the time was 8 to 20 times higher than pre-industrial levels. It is difficult to establish the exact cause, but one plausible hypothesis is that non-vascular plants settled and developed on land during the late Ordovician. This major modification of the biosphere would have accelerated the process of silicate alteration on the continents. This process, by fixing very large quantities of carbon dioxide, would have led to a decrease in the Earth's temperature and the development of polar caps. The consequences continue, since the ice sheets increase the albedo of the Earth, reflecting more of the sun's rays, thus aggravating the drop in temperature. Another theory is that a large continental volcanic activity has caused basaltic flows in the Cattian igneous province. This tilting is at the transition between a period where the continental masses were very dispersed and where a warm climate prevailed, and a cold period that begins during the Cattian and will culminate with a Hernantian glaciation caused by the migration of the supercontinent of Proto-Gondwana to the South Pole. These volcanic activities would have released large quantities of CO2 into the atmosphere and would have replaced granitic rocks by basaltic plains. The problem? Basaltic rocks erode much faster than granitic rocks, which means that they store much more atmospheric CO2. Soon the level of atmospheric CO2 decreased, falling below the levels of pre-volcanic activity. However, this glaciation caused the sea level to drop by several hundred meters. Average global surface temperatures dropped from 30 degrees Celsius to 10 degrees Celsius, or from 86 degrees Fahrenheit to 50 degrees Fahrenheit. Creatures that had made their homes in the deep ocean would have witnessed the cooling and shrinking of their habitat, and would have found themselves without a way out. The rate of extinction of marine animal families in the Upper Ordovician over about 20 million years is the highest ever recorded in the history of the Earth, on the order of 20 families per million years. The glaciation lasted between 1 and 35 million years. The survivors would have had a hard time recovering in these chemically hostile waters. Once the sea level started to rise again, the levels of dissolved oxygen in the water decreased, which would have increased the absorption of toxic metals in the oceans. This anoxia would have killed many of the survivors of the first wave of extinction. Following this extinction occurs a new geological phase, the Silurian. Over millions of years, CO2 is gradually re-injected into the Earth's atmosphere, warming the planet and ending the Ice Age. After this mass extinction, life proliferates again in the ocean. It proliferates and diversifies. Coral reefs can be admired, especially near the coasts of the Panthalassa Ocean and those of Paleotethys on shallow seabeds. The climate is mild, 20 degrees Celsius or 68 degrees Fahrenheit on the thermometer. The corals, especially the roughy and the tabulate, are very happy in the sea. The first one has a calcareous skeleton, a rocky element. It was solitary and becomes more and more colonial, hence the constitution of reefs. For the second, its exoskeleton, an external skeleton, is made of calcite. Did you notice the fish that just broke away from us by moving behind the corals? It is the Pharyngolepis oblongus. It belongs to the family of anapsids. It measures about 25 centimeters. If it has an anal and caudal fins, it does not have pectoral fins, but bony spines. It is undoubtedly a means of protecting itself from the predators for this fish, which feeds on the ground in the marine funds. A little further on, you will be able to see another kind of fish that also populated this part of the oceans. These jawless fish are part of the species that lived in saltwater, but also in the freshwater of rivers. Do you notice the cranial shield of this Adiolaspis tessellata? Despite its needle-like shape on a good part of its body, it is indeed a fish. It has two fins that allow it to move in the water. We also find other fish of the same type, like the Cephalaspis, which appreciates the estuaries thanks to its cranial shield. But this was not its only use. Indeed, his shield had sensory plates along the edge and center, which were used to detect the presence of worms and other burrowing organisms in the mud. But during this period, it wasn't just jawless fish. Quite the opposite. This famous jaw, which starts from the second branchial arc, are the acanthodians with spiny fins and the placoderms whose front of the body is enclosed in a bony carapace. Some of these fish had a bony skeleton, others rather cartilaginous. They are numerous and very diversified in this branch. You can see here Cheracanthus murchisoni. But we will fix our attention on this Climatius. It is a spiny shark. Rather good swimmer, it was also a fine hunter. It feeds mainly on other fishes, but does not make the fine mouth in front of a crustacean. What is rather surprising about him is precisely his jaws. The lower jaw is equipped with multiple sharp teeth. At the slightest sign of wear, the teeth fall out to make room for a new, perfectly sharpened tooth. The upper jaw has no teeth at all. Another category of creatures marks the Silurian. They are the Eurypterids. They already existed in the Ordovician. This beautiful specimen measures already 2.5 meters, that is 8 feet. It is the largest arthropod known so far. In addition to having rather extraordinary dimensions, it had a fast and efficient swimming technique. Its last pair of legs constituted real paddles, while its abdomen undulated, to make it gain in speed and mobility. As for feeding, it also had some assets to get by in the sea. Its chelicerae, small appendages located on the skull in the shape of a hook or a claw depending on the species, are nestled under its head when it is at rest. But in case of hunger, it projects them on its prey. These two cephalopods should undoubtedly be wary. Phragmocharis eurystoma and Phragmocharis dubium have a pretty shell, curved in the shape of a Phrygian cap. But it will be of no use facing the monster which prowls in these waters. The armored fish have made their grand entrance. These fish have a thick bony armor on their head and thorax. The plates of this armor allowed them to protect their vital organs, such as eyes, brain, heart, etc., from attack by predators, and perhaps sometimes even fellow fish. These fish were not very difficult. They frequented reefs, deltas, as well as the open sea. Their diets were just as varied. Some grazed on algae, others crushed mollusks, others were carnivorous. Entelognathus primordialis is one of the first placoderms. Its head and its body were covered with thick plates, while its tail carried scales. It had jaws but no teeth, and its small eyes were buried in large deep sockets. Each new geological phase has its milestone and a new facet of the Earth. This time it is the appearance of mountains in two different places. The first orogeny, phenomenon of mountain formation, takes place in the Lapitous Ocean after the collusion of two continents, Laurentia and Avalonia. The second also includes Laurentia and Amorica. Two oceans close, the Lapitous and the Rake. Elsewhere, they are slides of oceanic plates under neighboring plates that occur. Several physical reactions follow one after the other, making the world evolve. The temperature has increased considerably and is approaching 30 degrees Celsius or 86 degrees Fahrenheit on Earth. It must be said that with our heads underwater, we have not seen how much things have changed on the surface of the continents as well. Vegetation has grown a lot, and photosynthesis is working, so carbon dioxide levels are falling. The vegetation is small for the moment, but during the Devonian period, we find the beginnings of the forest. Stromatopores, tabulate corals, and tetracolariar corals continue to build the reefs. They are growing, diversifying, organizing themselves, and can thus welcome and shelter new species. Brachiopods and other shell specimens are still evolving in Devonian waters. The armorfish proliferate. We can see here a Brothriolepis, and a little further, a Dunkleosteus. Let us approach first the Bothriolepis. This one seems to be a Bothriolepis canadensis, to be precise. It is a small benthic animal. In other words, it roams the seabed. It prefers fresh water and is part of the detritivores. This small marine animal feeds on animal, plant, and fungal debris. In short, any organic element in decomposition. It measures about 30 centimeters or 10 feet in general, but can reach 100 centimeters or 40 inches for the largest species, Bothriolepis maxima. Let's take a closer look at Dunkleosteus, which is part of the placoderm family. Dunkleosteus was an armored fish. The armored fish, if they appeared in Silurian, reigned supreme in Devonian. They became the kings of the oceans and challenged the great Eurypteroids, which until then were the most dangerous predators. One of the most formidable of these armored fish is the Dunkleosteus. This cartilaginous fish is one of the first of the genus Condycthyes. It has paired fins, paired nostrils, scales, and a serial chambered heart. You see the fins. They go in pairs on each side of its body. It has quite large eyes and small but sharp teeth. It feeds on fish and can live in a group. This one must be Cladocelicae elegans. Despite its size between 60 and 180 centimeters, that is to say between 20 and 70 inches, it is the favorite prey of the mastodon of the seas, the Dunkleosteus. The fish with radiated fins continue to populate the oceans, like this Actinopterygenian, Carolepis. Others, like the fish with fleshy fins, have undergone an extraordinary evolution. It is the lungfish. They are pulmonate fish. In addition to gill breathing, these fish have a lung. This kind of fish knows very different morphologies. Here is a Lepidosaurin, Paradoxa. Rather long, it has a median fin which surrounds the posterior part of the body. It also has pectoral and pelvic fins, but they look more like thread-like excrescences. Here is another congener of the same family, the Neoceratodus forsteri. It is much more stocky, but it is indeed part of the same family. Another particularity of this fish is its ability to breathe in the open air, with as much ease as going down to 30 meters or 100 feet underwater. It is able, for example, to crawl in the mud, or for certain species of lungfish, to create a burrow in the mud, to manufacture a cocoon by secreting a mucus which seems assimilated to a living tissue with antimicrobial properties. All these extraordinary faculties have undoubtedly helped it to survive, in spite of the climatic and physical changes that the planet has undergone over the millions of years that followed. On the geological timescale, we are now between -359 and -299 million years. It is during the Carboniferous period that Pangea appears. Almost all the continents are welded into a single continental mass. Another element to remember about this geological phase is the important transgression of the warm waters of the Paleothus on the continental platforms. It allows many coral reefs to develop. Erosion also brings many changes. It favors the formation of mountains, but also vegetation. The amount of CO2 will therefore largely decrease, and at the same time, lower the temperature of the planet, which is now about 15 degrees Celsius or 59 degrees Fahrenheit. If the family of arthropods, like the Trilobite that we were able to discover in the Cambrian, is losing speed and is coming to an end, other marine specimens continue to evolve. Because of the constitution of coral reefs, the population of certain groups of marine animals proliferates. Brachiopods, echinoderms, and mollusks, for example, reside in these warm waters. Here is a member of the brachiopod family, the Productus subaculeatus. Its shell is very small, between 12 and 24 millimeters only. It walks not far from what looks like a plant from afar, but which is not quite one. Crinoids have a morphology that reminds a plant. It is to this resemblance that they owe their name. Crinoid means sea lily. The stem can be more or less long and the roots are fixed in the seabed. At the other end we can see a crown. It is made up of the various branched arms of the crinoid. It is a real shelter for many marine animals, like gastropods, for example. If its arms form a refuge, they also allow it to feed on plankton by filtration. The stem constitutes a calcareous skeleton. This specimen, as you may have guessed, is part of the shark family. The most impressive thing about this fish is without a doubt its jaw. Look closely. You will notice that its lower jaw is shaped like a circular saw. This does not bode well for other small vertebrates that cross its path. Predators, or a charming asset for the reproduction period? Difficult to say. This specimen is one of the first cartilaginous fish that swam in the ocean. It shares this small feat with a Cladocelecki and the Gladbacchus. It appreciates very much small fishes, but also primitive amphibians that it managed to hunt without too much difficulty. We now come to the last geological phase of the Paleozoic, the Permian. This period is between -299 and -251 million years old. Pangea is finished. The temperature oscillates between 15 and 18 degrees Celsius, or 60 degrees Fahrenheit. Oxygen in the atmosphere continued to increase, no doubt thanks to the vegetation of the continent, which continued to conquer the smallest square kilometer on the surface. The reefs are a real marine breeding ground. They are essential for the survival of many species. Corals, of course, help their development, but they are far from being the only ones. In this intertropical zone, you can see a big yellow sponge. No, it is not a rock, but a gigantic sponge. This one is probably around 2 meters or 6 feet. Many filter feeders reside here. We can see brachiopods, but also mollusks. The one you see here is Cuperoceras texanum. As you can see, this species has developed spines all along its shell. This provides an effective defense against certain predators. These fish with cartilaginous skeletons have been around for several million years now, and they continue to develop in the Permian. They have muscles adapted for swimming, increasingly developed sensory organs, and a powerful jaw. Hybotus is very similar to the shark we know today. It could reach 2 meters or 6 feet in length. An outstanding predator, its morphology allowed it to hunt many types of prey. The shape of its teeth allows us to believe that it fed as well on fish as on other marine animals. Here is another specimen of the same family. Despite its appearance, Orthocanthus is indeed a primitive shark. It has a rather long and slender body, but it also has sharp teeth. Unlike the previous fishes, these are fishes with a bony skeleton. Another specificity of this family of vertebrate fishes, the rhyid fin, i.e. with a rigid bony part. Here is Adula blainvelli. It measures between 5 and 20 centimeters, or between 2 and 8 inches, for the adult specimens. Its dorsal fin is in the continuity of the anal fin. It also has ventral fins, but they are rather small and thin. It was undoubtedly a good swimmer. This faculty was surely an essential survival technique in order to flee its numerous predators, like Actinodon, a temnospondyli amphibian, or sharks, like Exploricanthus. We have not mentioned this family until now. It appeared in the Carboniferous, but it developed mainly in the Permian and Triassic. Some of them are only a few centimeters or feet long, while others are close to 10 meters or more than 30 feet. As you can see, this category is very varied. As incredible as it may seem, in this class there is a family of temnospondyls. They are carnivorous and have made a place for themselves on land, as well as in the sea and freshwater. Here is one of them, an Eriops megacephalus. It is quite impressive, isn't it? It can measure up to 3 meters or 10 feet and probably weighs more than 200 kilos or 440 pounds. Its huge mouth doesn't let you know what's inside. But if you get a little closer and open its jaw, you will see that it has many curved teeth. Incredible for an amphibian, right? They also have an enamel with a pleated pattern. Even its palate is formidably equipped. There are 3 pairs of fangs curved backwards. It's a real trap for even the slippery prey. None of the aquatic animals that we met seem to realize the drastic changes that are taking place and the serious consequences that they are about to undergo. The reunion of all the continents in a single block causes a generalized reduction of the sea level. The formation of pangea thus leads to the reduction of the surface of the seas, which were largely populated. The sea level drops by 250 meters, or more than 820 feet. The seas are then shallow, the waters stagnant and warm, poorly oxygenated, and therefore unfavorable to animal life. The warm currents around the South Pole and the increase in the CO2 content of the atmosphere have allowed the polar cap that used to cover the pole to melt. These changes lead to others. The ice caps are no longer there, or too few of them to reflect solar energy back to space. Intense volcanic eruptions follow one another and enrich the atmosphere with CO2. Global warming is underway. The greenhouse gas has combined with CO2 to increase the intensity of this warming even more. The increase in ocean temperatures has destabilized the methane deposits stored in the ocean floor. Huge eruptions of basalt are taking place in Siberia, spitting more and more CO2 into the atmosphere. The greatest biological crisis of all time is underway. Nothing can stop it anymore. Much less known than the disappearance of non-avian dinosaurs, the Permian Triassic crisis is nevertheless the most deadly. The Permian Triassic extinction is one of the most deadly, perhaps even the most severe, that the world has ever suffered. 90% of marine species, 75% of vertebrates, almost all primitive amphibians will be wiped off the face of the Earth. After this crisis, nature takes its rights. Life takes its course. Nothing is simple. It takes time. But nature is amazing. We are now entering the Mesozoic. It is located between -251 and -66 million years. If the beginning of the Paleozoic marks a turning point for living organisms thanks to the appearance of specific cells, the Mesozoic witnessed the emergence of new species such as mammals, birds, dinosaurs of course, and angiosperms. The latter are plants that can form flowers and fruits. This phenomenon has an enormous impact on the terrestrial ecosystem. Divided into three periods, the Triassic, the Jurassic, and the Cretaceous, the Mesozoic began on a single continent, Pangea. Then, as the periods progressed, lands were to break up, fall apart, drift apart, and create the geographical world we know today. In the Triassic period, all the continents were united in a single land, called Pangea. But little by little, two groups separated to give birth to Laurasia and Gondwana. The climate, the fauna and flora have adapted to these new conditions. At the base of the food chain, we find sponges, polyps, crinoids. Insects will also become more and more abundant, especially in the Jurassic. These animals allow others to survive, especially fish. We are here during the first phase of the Mesozoic. On the geological timescale, the Triassic is between -252 and -201 million years ago. The average temperature is 18 degrees Celsius, or 64 degrees Fahrenheit, but it can vary depending on the region. Some are desert, others are affected by the monsoon. The icy areas are very sparsely populated. The temperate areas are already more livable. But it is especially in the tropical zones that life is the most effervescent in the ocean. The atmosphere consists of 18% oxygen, but contains very little CO2, only 0.25%. The climate was warmer. During the entire Mesozoic, the Earth did not experience glaciation. The ocean tries to reconstitute the reefs, the first underwater habitat for a large part of aquatic species. Tetracorallian corals have been largely wiped out. Little by little, hexacoralliar corals are taking their place. Here you can see calcareous algae supporting the corals in the hard work of building a reef. Soon life will be able to flourish again. In the Triassic, species that had tried to develop in the Permian finally managed to make a place for themselves in this world. Ammonites and sea urchins, for example, diversify and proliferate. Look, right there. You can see a Crioceratites emerisy. It is part of the ammonites. It is called unrolled ammonite. You can probably understand why. Its shell rolls up on itself and forms an effective protection against certain predators. A little further on, another ammonite, Ceratites semiparatus goes in search of food. The Mesozoic is often called the Age of Reptiles. In the Triassic period, this group of reptiles looks a bit like dolphins. They are Ichthyosaurs. There is a Californosaurus, and a little further on, an Nothosaurus. These marine specimens were between 1 and 10 meters long, that is to say, between 3 and 30 feet long. They fed exclusively on fish. As you can see, these species were viviparous. This female is in the process of expelling her young. In the predator category, Ichthyosaurs had to share space with Nothosaurus. This reptile is semi-aquatic. It is a Nothosaurus. It looks a bit like a lizard. Look closely at its legs. They are equipped with webbed toes. It can therefore easily swim, but also move on land. It has a long neck, a long snout, and very fine and pointed teeth. Its tail was used as a propeller to move in the water faster. Its favorite food is fish, but it sometimes feeds on other marine animals if it has nothing else to eat. Even if it is adapted to swimming, it lays its eggs on dry land. It is not fully adapted to aquatic life, although it does quite well in the water. It lives on the shore and spends part of the time out of the water when necessary. Here is Plesiosaurus calgagni, which presents itself to us. In it, we don't see any toes anymore. They have been replaced by real fins. As you can see, his neck and his tail are very long. He is a very good swimmer, and he is also very fast in the water. This is a valuable asset for hunting. It lives in lagoons alongside the Nothosaurus, the Pachypleurosauride. It is one of the largest marine vertebrates of the Triassic. These small water lizards lived only in the Triassic. Here is a small Chycosaurus. This elongated animal could be up to 1 meter or 3 feet long. Its limbs are paddle-shaped. They allow him to move in the water with a disconcerting ease considering his size and weight. In the family of Pachypleurosaurs, we also find the Anerosaurus and Dactylosaurus. They are the first of this family to have lived in Europe. The Serpianosaurus lived in the same regions. We will now have to leave this small world to discover the Jurassic. The Jurassic follows directly after the Triassic. This period is very favorable to marine species. The transgression begins and invades a large part of the continents. You must first observe the flora in order to note and understand the changes that took place. Radiolarians, such as Ellipsocophus or Saturnalis, are unicellular planktonic animals a few hundred micrometers in diameter. They provide the silica necessary for the green algae that proliferate. Radiolaria would have appeared in part thanks to underwater volcanic eruptions. These small and complex organisms are as useful as they are beautiful. Look at this, Sagonacena stellata. When the soft parts die, this is what you can find as a structure under the sea. This is its skeleton. The star formation is magnificent. These small, radiolar organisms abounded in the Jurassic. The most likely reason for this abundance would be the upwelling of deep cold water. Rich in nutrients, they bring back to the surface of the ocean many nutrients. Radiolaria are also symbiotic species. Algae, unicellular or dinoflagellate, live in harmony with these siliceous marine plantlets. In the middle of these algae lives a Hildoceras bifrons. This small predator catches its prey with its tentacles. For the moment, it does not seem to be hunting. He surely had dinner a short time ago. That leaves us all the leisure to observe it a little more closely. Its shell is in flattened spiral. You notice that it is very ribbed and all in relief. Inside there are chambers. These are filled with air and allow the buoyancy of our Hildoceras bifrons. This specimen is probably a female. The females are bigger than the males. They measure between 95 and 175 millimeters, while the males do not exceed 40 millimeters. Here is a Stenopterygius. It is part of the Ichthyosaur family that we have already met. Its appearance and behavior are very similar to those of dolphins. It swims most of its time in deep water. It hunts and feeds on fish, but also on cephalopods, mollusks equipped with tentacles. The specific cells have largely developed and refined since the Cambrian. Our Stenopterygius has a skin composed of two distinct layers, the epidermis and the dermis. It also has a layer of fat that allows it to preserve the internal temperature of its body. But let's not linger too long. We have an appointment with a Plesiosaurus, and he doesn't like to wait. Here is Elasmosaurus platyurus. He is a member of the Plesiosaur family, the long-necked marine reptiles. This one is 7 meters or 22 feet long, but it can easily reach 15 meters or 50 feet as an adult. Inside its neck are more than 32 cervical vertebrae. One would think that their barrel-shaped body, long neck and small legs would not help them much in the ocean. But despite appearances, this sea monster is quite agile and very powerful. First of all, its legs are also fins. These allow him to swim a bit like turtles. It explores the oceans and does not limit itself to a given territory. It is lively and has a very powerful jaw. It quickly became a feared predator in the 4 corners of the globe. 2.4 billion years ago, the Earth experienced its first ice age, which was also one of the longest in its history. This was the Huronian glaciation. This glaciation began 2.4 billion years ago and lasted until minus 2.1 billion years during the Paleo-Proterozoic era. The oceans occupy almost 25% more than their present volume due to the degassing of the Earth's mantle. Lava from volcanic sites is rich in potassium and phosphorus, making it a high-quality fertilizer. Due to wind and weather, lava naturally breaks up and crumbles. Small pieces of material embed themselves in the fractures of the magmatic rocks and accumulate there in large numbers. As the rocks are porous, they retain not only moisture, but also a warm temperature ideal for the development of life. In the end, these seemingly inhospitable places were the scene of the development of the first organisms. Among these microbes carried by wind, weather, or tides are cyanobacteria, a type of prokaryotic bacteria with no nucleus. These unicellular organisms can live both in water and on land, in large colonies. Their metabolism is based on photosynthesis. They produce oxygen. Cyanobacteria in the air transform nitrogen into ammonium and nitrate, while those in the oceans trap carbon and produce the limestone of stromatolites. The combination of lava fragments and cyanobacterial growth gradually forms soil. Then, little by little in these same privileged environments, more complex organisms such as mosses and fungi appear. The latter will develop a method of rooting, in particular, mycenes. It was thanks in part to them that life first walked the Earth, since by breaking rocks they enabled the first terrestrial settlements. It was only later that pollen also contributed to the proliferation of life. The Earth is not yet very conducive to the development of more complex forms of life. It is covered with active volcanoes, and toxic clouds are permanently present. Vast expanses of lava cover the ground as the sun floods in its deadly ultraviolet rays. Although cyanobacteria remain in the water, the flora is still widely dispersed. Nevertheless, a major event occurred 2.4 billion years ago that changed the face of life. It was the Great Oxidation. At that time, oxygen in the Earth's atmosphere was scarce. It remained trapped in minerals or enclosed in water. The Great Oxidation affects the Earth's waters, biosphere, and atmosphere. It can be seen as a catastrophe or an opportunity for life on Earth. Most organisms are anaerobic, but cyanobacteria are beginning to develop oxygenated photosynthesis. They occupy a new ecological niche and reproduce very rapidly by harnessing the sun's energy. Photosynthesis produces a waste product, oxygen, which cyanobacteria expel into the air. Initially, this oxygen is absorbed by the oxidation of surface iron, but as the number of cyanobacteria increases, the oxygen sinks, becomes saturated. This accumulation of oxygen in the atmosphere has had devastating consequences for anaerobic organisms, which cannot survive in the presence of oxygen. Oxygen is a highly reactive element that can disrupt the metabolic processes of anaerobic organisms by forming free radicals. These unstable molecules can damage proteins, nucleic acids, and cell membranes, leading to cell death. As a result, many of these organisms have been eliminated, leading to a mass extinction of anaerobic organisms. But increased oxygen levels have paved the way for the evolution of new life forms better adapted to these conditions. Oxygen enables much more efficient cellular respiration than other forms of energy metabolism. In other words, organisms capable of aerobic respiration can produce far more energy from a given quantity of nutrients than their anaerobic counterparts. Some organisms have evolved to use oxygen as the final electron acceptor in their electron transport chains, thereby greatly increasing the efficiency of ATP production, which could be described as the cell's energy currency. In addition, antioxidant enzymes such as superoxide, dismutase, or catalyses have evolved to neutralize toxic free radicals produced by reactions with oxygen, enabling these organisms to survive and thrive in an oxygen-rich environment. In order to survive, aerobic organisms have learned to use oxygen to breathe, eliminating the free radicals that can oxidize molecules and damage their bodies. This evolution was made possible by 3 new amino acids integrated into their genome: methionine, tryptophan, and selenocysteine. Since then, all aerobic organisms have learned to survive in the presence of oxygen, provided it remains at normal concentrations. If it exceeds these concentrations, oxygen remains unconditionally poisonous. Although this change of atmosphere was fatal to most life forms of the time, new organisms were emerging in the form of eukaryotes and metazoans. Eukaryotes include all organisms, whether unicellular or multicellular, as long as they contain a nucleus and organelles specialized for respiration. Today, eukaryotes encompass three major kingdoms of the living world: plants, fungi, and animals. The second group of organisms to develop is the metazoans. They are multicellular, consisting of a nucleus and organelles, and feed on organic matter. Their cells form tissues. The atmosphere is totally destabilized. Microorganisms have consumed most of the nutrients they needed to form oxygen. But there was another consequence for the climate. During this great oxygenation event, atmospheric oxygen increased considerably, thereby reducing methane. Oxygen combines with methane to form carbon dioxide and water. The latter do not retain heat as well as methane. At the same time, a mass extinction occurred for the majority of life forms, which were then anaerobic. For them, oxygen was toxic. At the same time, volcanic activity slowed for 250 million years. These events combined to produce less carbon dioxide in the atmosphere, resulting in a greatly reduced greenhouse effect. Temperatures fell, and the planet entered an ice age. For the first time, the Earth's surface would have been entirely covered in ice. This abrupt change in climate is linked to the transformation of the atmosphere that occurred with the evolution of life. Photosynthesis processes carried out by prokaryotic bacteria released oxygen. At the same time, the limestone that forms traps CO2, considerably reducing its quantity in the atmosphere. The reduction in greenhouse gas emissions led to a drop in the Earth's temperature. At that time, the sun provided only 85% of the energy it does today. Temperatures reached as low as -50 degrees Celsius or -58 degrees Fahrenheit for tens of thousands of years. The water present at the time becomes ice. Albedo increases, accentuating cooling and freeze-up. For millions of years, the Earth resembled an enormous ball of ice, with a surface temperature of -10 degrees Celsius or 14 degrees Fahrenheit. Scientists believe that this Huronian ice age brought photosynthesis to a virtual standstill. The Huronian glaciation occurred at a very early time in the Earth's history, long before the existence of dinosaurs or most of the life forms we know today. Its probable consequences have been erased by the billions of years of geological evolution that followed. The evidence of this period has been overturned by subsequent geological changes. Nevertheless, scientists have been able to trace the formation of vast glacial deposits. These accumulated in the form of sedimentary rocks, principally tillites, formed by the compaction of continental sediments containing material carried by glaciers, and lamanites. Glacial activity modifies the landscape, forming lakes and valleys. Such a drop in temperature must also have altered ocean circulation and atmospheric composition. Glaciation also had a geochemical influence, modifying the cycle of elements such as iron and oxygen in the oceans. Finally, this change in climate imposed difficult survival conditions on the life forms that remained at the time, and this certainly had an impact on their evolution, as well as on future life forms. And yet, life survives the cold. In principle, below the freezing point of water, the metabolic functions of organisms are interrupted. As water crystallizes, it invades the cytoplasm in organisms. Cell tissues are destroyed, and the organism dies, yet microbial life can persist in such a seemingly hostile environment, and the return to life following the ice ages is proof of this. When imprisoned in ice, some microbes continue to metabolize at a much lower rate than normal, depending on the temperature and quantity of food available. Others suspend all energy consumption or form spores to survive in the absence of energy. As conditions improve, mechanisms are put in place to repair cellular damage. Microbial life faced with starvation will react in different ways. Some organisms will suffer, while others will react in different ways. They may develop ultra-microcells, synthesize stress proteins, or express starvation genes to become more resistant. Another solution is to reduce metabolism and become dormant, or to form spores. Cold shock and falling temperatures also place different demands on microbes. They will develop methods to counter the loss of membrane fluidity, the reduced rate of enzymatic processes, and cell damage. Ice subjected to extremely low temperatures, such as during glaciations, displays unusual properties. Liquid veins can be found. These are insoluble impurities in the crystalline structure that concentrate in the liquid phase and form a vein-like network, measuring just a few micrometers. These famous veins contain liquid water, nutrients, and biomolecules, a veritable oasis for the metabolism of the microorganisms trapped there. However, microbes must be able to tolerate a pH as low as 0 if they are to benefit from the energy present in acidic ice veins. The acidophiles most frequently found in liquid veins are eukaryotic cells, bacteria, and archaea. There is also a surface of mineral grains dragged along by the ice, which develops a thin film of water that remains in a liquid state. This allows microorganisms to extract nutrients and the energy they need. They will have to adapt to keep their cytoplasm fluid, even when confronted with a temperature of -50 degrees Celsius or 58 degrees Fahrenheit. Despite the catastrophic situation that befell the Earth during the Ice Age, its heart continues to be active. The CO2 emitted by volcanoes accumulates under the ice and is suddenly released into the atmosphere, reinforcing the greenhouse effect and raising surface temperatures. Deglaciation then takes place in just a few tens of thousands of years. Volcanoes have also helped preserve life. They have kept certain areas out of the ice. Thanks to them, many species have been able to survive episodes of glaciation. As soon as the climate becomes milder again, species gradually colonize the regions surrounding these geothermal refuges. Studies carried out in the vicinity of these geothermal zones have shown a richness of biodiversity that diminishes with distance. Hundreds of millions of years have passed since the Huronian glaciation. The Earth has since been rebuilt. 800 million years ago, it consisted of a single vast continent, Rodinia, surrounded by a gigantic ocean, Merovia. At that time, the average temperature was 10.5 degrees Celsius, or 51 degrees Fahrenheit, and the young sun emitted 6% less light than it does today. The day lasted less than 22 hours, and the year comprised 13 months. Present-day North America forms the heart of Rodinia. Australia lies at our latitudes and Antarctica almost at the equator. As a result of magmatic movements and volcanic activity, Rodinia began to fragment around 750 million years ago. Initially, it split into two blocks, in the middle of which a new ocean, Panthalassa, the ancestor of the Pacific Ocean, was born. The part that today represents North America heads towards the ice-covered South Pole. The land in the northern half of Rodinia heads towards the North Pole. Between the two halves lies the Congo Craton. This is a hard, stable zone that was once consolidated to the lithosphere. A few million years later, these three parts will come together again to form a new supercontinent called Panatee. The collisions associated with this future meeting will give rise to mountains, the Pan-African orogeny. At this time, the mid-oceanic ripples are not very active, and average temperatures are falling. During the Varanger glaciation, the Earth actually underwent two glacial episodes. The first, known as the Sturtian glaciation, began 720 million years ago and ended 660 million years ago. Over the next 10 million years, temperatures rose again, forming an interglacial period. The second glacial episode, known as the Merino glaciation, occurred between 650 and 630 million years ago. These periods of severe glaciation are recognized as the most severe in Earth's history. Since the last ice age, the Earth has seen a resurgence in the diversity of life. There are new types of algae, such as chromophytes, an evolutionary grade grouping organisms with chlorophyll, but also haptophytes, a division of unicellular algae characterized by the presence of a particular extremity called a haptonym, or dinoflagellates, a class of highly diversified unicellular aquatic eukaryotic organisms. There are also hyphae, the filaments that make up mycelium and fungal spores. However, no traces of animals such as hydras or sponges have been found during this period. The parts of ancient Rodinia that reach the poles are not warm. Vast expanses of ice take shape. Soils and oceans freeze over hundreds of meters. Polar caps reach the equator. A feedback loop begins as ice reflects more of the sun's rays than darker oceans. The entire planet freezes over. Temperatures plunge to minus 50 degrees Celsius, and the thickness of ocean ice reaches over a kilometer. The Earth literally becomes a snowball. The distribution of carbon undergoes profound changes, leading to a reduction in oceanic organic productivity. Photosynthesis is halted for millions of years. Runoff water is no longer an agent of erosion. The atmosphere on Earth is distressing. The sun, although present, shines less brightly. The air is dry, cold, and unbreathable. Snowfall is rare, but powerful winds bring a little dynamism to this desolate land. No liquid water circulates. The situation seems catastrophic for life, and yet, at the bottom of the ocean, life persists in the form of algae and bacteria. And not only does it persist, but multicellular organisms also took off just after this ice age. How was this possible when everything seems so unfavorable to the concentration of nutrients and oxygen needed to sustain life? Scientists have carried out computer simulations to reproduce the snowball effect with an equivalent rate of glaciation. it appears that near the equator there are still refuge zones where the ocean would not have frozen. This is how extremophilic organisms were able to isolate themselves in a closed environment. In the end, evolution continued and even accelerated. Microbial life could even survive and develop in solid ice. Glaciers would have played a local role in oxygenating the oceans. Certain metals, such as iron and manganese, were overrepresented in oxidized forms, testifying to a significant local supply of oxygen. The farther away from the grounding line, the rarer the oxidized forms. The grounding line is the zone between the part where the ice floats and the part where it rests on land. During this ice age, the grounding line may well have been a veritable Eden filled with oxygen. This oxygen came from small air bubbles enclosed in the compacted snow that formed the glaciers. At the grounding lines, these bubbles were released into the liquid ocean as the ice melted and rubbed against the rough bedrock. Even as the ice descends to the equator, volcanism continues, and CO2 and methane are constantly being emitted into the atmosphere. Once the concentration of carbon dioxide reaches 350 times today's level, the greenhouse effect becomes sufficient to reverse the glacial situation and melt the ice. Life can resume. Work carried out by Noah Planavsky in the United States reveals that the erosion of continents during the melting of the ice released large quantities of phosphorus. Its high presence in the ocean would have contributed to the proliferation of phytoplankton and consequently the release of oxygen into the atmosphere. 1 million years, that and the Ediacaran fauna resemble jellyfish, arthropods, or leaf-like forms. Some resemble nothing known today. Most of the fossils found at this time do not fit easily into today's phyla. Cells, which until then had reproduced by dividing, were now able to stick together, thanks to a protein called collagen, to form the first multicellular animals. The latter are reduced to their simplest expression, i.e., a simple cluster of cells brought together for the benefits they all derive from it. There are no nervous, vascular, or digestive systems as yet. The sponge is the oldest animal known to have come into existence. Today, this living fossil numbers some 10,000 species. The sponge's body is soft and pierced by numerous tiny holes called pores. It is through these pores that the water passes and is filtered to extract the nutrients the sponge needs. The body is supported by a skeleton composed of limestone or silicon. Sponges have an extraordinary capacity for regeneration. Once a part has been removed, it grows back without being damaged. Sponges have a very wide distribution, having colonized both fresh and brackish marine waters to depths of over 5,000 meters or 16,400 feet, as well as shallow waters, regardless of climate. After a period of calm, the climate became capricious again, and a new glaciation occurred during the Upper Ordovician and Silurian periods, around 460 to 420 million years ago. During the Ordovician period, which began 485 million years ago, the continents were grouped together to form the supercontinent Gondwana. This was formed by the fracturing of Rodinia. The history of our planet is punctuated by the merging and separation of its land masses under the effect of plate tectonics, and the continents never stop moving. While Gondwana settles at the South Pole, 3 other smaller continents, Laurentia, Siberia, and Baltica, and their islands head north to find a warm home near the equator. Here they experience the vagaries of a tropical climate, a hot sun and violent rainfall. The rain that falls from the sky carries with it carbon dioxide from the atmosphere. Combined with the heat, the rocks are dissolved. Carbon-containing ions are released and carried by runoff into the oceans. Marine animals use them to build their shells and skeletons. When they die, the carbonate material is stored in sediments on the seabed. In the long term, the process of taking carbon from the atmosphere and burying it on the ocean floor considerably reduces the amount of atmospheric CO2. The CO2 released by erupting volcanoes is not enough to compensate for these losses. The greenhouse effect diminishes, and temperatures on Earth begin to fall too. This ice age is not, however, an icy one. We're not talking about a snowball Earth here. It's even likely that in its early stages, it contributed to the development of biodiversity. During this period, the number of marine animal genera increased, known as the Great Ordovician Biodiversification Event, or GOBE. The rapid diversification of plankton favors the development of fauna living on the ocean floor. Cambrian trilobites, inarticulate brachiopods, and eucrinoids gave way to cephalopods, crinoids, and articulate brachiopods. Continental seas are shallow and rich in life, and the first coral reefs appear. Mollusks become common, especially bivalves, gastropods, and nautiloids. Corals appear, colonizing the oceans and building immense reefs like veritable ecosystems. They helped enrich the marine fauna. By the end of the Ordovician period, the oceans were teeming with species, each more diverse and varied than the last. From starfish and sponges to sea scorpions and other extraordinary species of clumsily swimming primitive fish. It was also at this time that the first large predators appeared. Until then, animals had been almost exclusively benthic, staying close to the seabed, but orthocerid cephalopods were the first to swim in open water. Trilobites had better watch out, because the terror of the seas is approaching. Here we see a Camaraceris. Sporting a straight cone several meters long, it has tentacles that it can wave from all sides. Its bulging eyes enable it to spot its prey in search of its next meal. With a single stroke of the beak, the carapace of a trilobite breaks in two. From now on, the entire food web becomes more complex. Biodiversity may appreciate the drop in temperature compared with the Cambrian, but it will have trouble coping with the next challenge. The Andes-Saharan glaciation contributed to one of the 5 greatest mass extinctions in Earth's history, known as the Ordovician Silurian extinction. Following this extinction, 70% of species disappeared from the Earth's surface. But what was the origin of this glaciation? Far away, several thousand light-years from Earth, a star exploded in a supernova. The gigantic burst of energy releases gamma rays that reach the Earth at the speed of light. These rays penetrate the atmosphere, altering the ozone layer and darkening the planet. Nitrogen and oxygen are transformed into the toxic gas nitrogen dioxide. The latter engulfs the planet to the point of blocking the passage of sunlight. This theory has little support in the scientific community, as the main obstacle to its acceptance is the difficulty of proving it, as traces of the supernova have long since disappeared. but another cause could have had an impact on the climate of the time. Although solar luminosity was around 4.5% less intense than today during the late Ordovician period, a decrease which under today's climatic conditions would lead to glaciation, the atmospheric concentration of carbon dioxide was considerably higher, reaching levels up to 18 times higher than today. This high CO2 concentration would normally have exerted a powerful greenhouse effect, counterbalancing the lower solar luminosity. Parallel to these factors, the Appalachian orogeny was underway, a geological process that spanned approximately 325 to 260 million years. This phenomenon was the result of the subduction of the oceanic tectonic plate beneath the North American continental plate. This geological process contributed to a massive reduction in atmospheric carbon dioxide levels. The explanation lies in the silicate weathering mechanism, a chemical reaction accelerated by the newly formed mountains, which captures carbon dioxide from the atmosphere and stores it in the Earth's crust. In addition, tectonic plate movements have led to significant changes in the distribution of continents, which may have influenced ocean and atmospheric currents, thus modifying the climate. To this we can add the Earth's orbital variations, which also have the potential to influence climate by altering the incidence of solar radiation on the Earth's surface. Whatever the cause, glaciation is underway. As ice accumulates on the continent, sea levels drop. Shallow marine areas are reduced. The first links in the food chain are affected, resulting in famine for all organisms. What was once an ocean teeming with life is totally devastated. In just over 500 years, a third of the existing fauna had disappeared. Another 100,000 years later, the famine continues. Glaciers sucked water from the ocean. Shoals are drained, drying up. The sea retreats several hundred meters, but once again life will prevail. Beyond a certain depth, organisms can find refuge. Nautiloids and eurypterids seek shelter on the seabed. Other animals adapt to cold water. Such is the case of the astrapus. This small primitive fish of the ostracoderm family, barely larger than a hand, has no fins and moves with the back of its body. To feed, it sucks up small invertebrates living on the seabed or the debris of dead animals. Its skin is highly sensitive to vibrations, enabling it to escape the predators of the time. Astrapus was the first to feature a primitive backbone. This creature, relatively insignificant at first glance, is in fact the first known vertebrate fish. This lineage would later give rise to birds, reptiles, and mammals. Astrapus proved particularly resistant to this new ice age. It follows the retreating ocean. It is a picky eater, feeding on whatever it can find. It also tolerates cold water better than other aquatic creatures. The astrapus adapts to this new ordeal, and soon a new variety of fish is born. These were equipped with the first gills, enabling them to absorb food more easily. It would be another 500,000 years before the planet began to warm up. At last, the glaciers melted. But for the species that had managed to survive the Ice Age, it was a new climatic upheaval. The toll was heavy. Over 70% of species disappeared forever. Thanks to nature's formidable resilience, life will resume and write a new chapter in the history of the Earth. The oceans will be repopulated by astonishing species, and the planet will gradually return to its tropical climate until the next ice age, which began in the Carboniferous period around 320 million years ago. We're in the Devonian over 400 million years ago. This was a pivotal period for vertebrates, but also for vegetation. The Earth is still mostly covered by the immense Panthalassa Ocean. Proto-Gondwana slowly slides northwards. It is set to collide with the young continent of Laurasia, formed a few million years earlier. These two continental blocks would unite at the start of the next period, the Carboniferous, to form a single continent, Pangea. At this time, the ice caps were absent, and the Earth enjoyed a relatively mild climate, around 25 degrees Celsius, or 77 degrees Fahrenheit. The weather was warm and vegetation thrived and conquered terra firma. The first terrestrial plants, characterized by lichens and mosses, appeared around 500 million years ago. Over millions of years, creeping plants evolved into ferns and lycopods, until during the Carboniferous period, over 350 million years ago, for the first time in Earth's history, they became rich in abundant vegetation. Thanks to warm, humid temperatures, the first insects proliferated. For the time being, they are the only terrestrial inhabitants. There are currently no herbivores. As a result, plants are literally colonizing the Earth. The first forests formed, vegetation diversified and became abundant. Large tree ferns grow alongside lycopods a few meters high. The first broad-leaved plants appear. Thanks to photosynthesis and the resulting oxygen, the Earth's atmosphere is enriched with oxygen, which will not be without consequences. Indeed, the rise in oxygen levels combined with high atmospheric pressure favored the most energy-intensive metabolisms, and large terrestrial vertebrates grew to titanic proportions. One of the best-known examples is the dragonfly, Meganeura, with a wingspan of up to 75 centimeters or 30 inches. There's also the Arthropods, a distant ancestor of millipedes, which measured up to 1.8 meters or 6 feet in length. Rising oxygen levels also led vegetation to become more resistant to fire. It was also at this time that flowering plants appeared. Increased plant development leads to the absorption of large quantities of atmospheric CO2, which considerably reduces the greenhouse effect. Lignin and cellulose from tree trunks and plant debris accumulate. A polar climate process is triggered. Summers are now too cold for winter snow to melt. The snow accumulates and creates sufficient pressure to form ice. Albedo rises as the ice sheet, an ice sheet covering the mainland, expands. A feedback loop is triggered, and the ice extends further and further. Under the effect of this climate change, plants are forced to slow down their evolution. The high oxygen level triggers fires despite the prevailing humidity. The combination of slower vegetation growth and the occurrence of fires causes a further increase in carbon dioxide in the atmosphere, preventing a snowball effect through greenhouse warming. Over the years, the drop in albedo leads to warmer summers and milder winters, limiting snow depth in areas where glaciers grow. The melting of ice caused by global warming leads to a rise in sea level, which now covers the anoxic zones that used to trap carbon. The Earth now has less surface area to sequester carbon, and a greater proportion of carbon dioxide returns to the atmosphere. The Karoo glaciation came to an end 260 million years ago, bringing the Earth's atmospheric oxygen levels close to those of today. Since then, there has been no ice age until the one we're currently in, the Pliocene Quaternary, which began around 2.58 million years ago. At the end of the Pliocene, today we are in the last Great Ice Age. It began during the Upper Pliocene some 2.58 million years ago. We are currently experiencing an interglacial period, which is reflected in the retreat of glaciers accompanied by global warming. The current ice age is known as the Pliocene Quaternary glaciation. Since its beginnings, the Earth has undergone several glacial and interglacial periods. Ice caps advance and retreat on timescales ranging from 40,000 to 100,000 years. In the past, they covered the entire globe. Today, they are limited to Greenland, Antarctica, and a few smaller glaciers, such as the one covering Baffin Island, 2.58 million years ago, the continents were roughly as they are today. Scientists estimate that they have not moved more than 100 kilometers, or 62 miles, in relation to each other since the beginning of this period. During the previous period, the main change was the connection between North and South America. As a result, the Isthmus of Panama is formed, causing the disappearance of warm equatorial currents and the onset of an Atlantic cooling cycle. The climate gradually became drier and colder. The Greenland ice sheet appears, while the Antarctic ice sheet thickens. The collision between the African plate and Europe continues. The Alps continue to orogenize. Combined with tectonic movement, erosion phenomena, and the trapping of atmospheric CO2 in the form of carbonates continue, reducing the concentration of CO2 in the atmosphere. These phenomena are leading to global climate change. Tropical forests are shrinking, with only a small portion remaining around the equator. Savannas and grasses are now conquering every continent. Temperate forests of deciduous trees are found at mid-latitudes, and conifers and tundra at high latitudes. Antarctica is a veritable frozen desert. The marine and terrestrial faunas, although primitive, are now modern. The junction of North and South America and the formation of the Isthmus of Panama have brought about a great deal of inter-American exchange. A wide variety of animals can now migrate from south to north and from north to south. Mammals, reptiles, amphibians, arthropods, and even flightless birds. Mammals, represented by rodents, mastodons, and opossums, are widespread in North America. We also find Gomphotherium, a now extinct species closely resembling today's elephants. It has 4 almost upright tusks and a short, tapir-like proboscis that falls back on the lower jaw. Sloths, glyptodons, and armadillos migrate northwards across the Isthmus of Panama. Carnivores diversify. They include dogs, bears, and canids. In Eurasia, while the presence of primates diminishes, rodents are widespread. Giant rodent species roam the planet's surface. A giant rodent fossil, Joseph-Fortigacea monesi, was discovered on a beach in Uruguay in 1987. It appears to be the largest and heaviest rodent known today. Its closest relative today is the pacarana, a rodent that weighs between 10 and 15 kilograms, or 20 and 35 pounds, and lives in the tropical rainforests of the Andes. Joseph-Fortigacea monesi, on the other hand, measures up to 3 meters or 10 feet in length and weighs up to a ton. His skull alone measures 57 centimeters, or 23 inches. In comparison, it's as tall as a bison. Its morphology is similar to that of a guinea pig, but proportionally the size of a hippopotamus. Its jaw is exceptionally strong. In Africa, primates continue to evolve, and ungulates dominate. It was also at this time that the first humans and giraffes appeared. The number of bovid species increases. For the first time since the Cretaceous, and thanks to the great Inter-American exchange, North American species mix with those of the South. Marsupials remain dominant in Australia. Wombats and kangaroos appear. Platypuses appear. As the climate changes, tropical flora is replaced by subtropical forests and grasslands. Western Europe was enriched with trees from the birch, oak, and ash families, as well as conifers further north. But the Earth is affected by a gradual cooling, and vertebrates are not indifferent. Evolution continues, but it's getting poorer. Perissodactyl ungulates decline. Conversely, the large artiodactyl ungulates fared much better, as they were satisfied with a coarse diet and better able to withstand periods of food shortage. Mastodons, these gigantic herbivorous mammals, proliferated, and the first elephants appeared. All these giants were an important source of food, and new larger carnivorous mammals appeared. Most of the fauna that reigned at the end of the Pliocene no longer exists today. The ice ages of the next few thousand years took their toll on many of these animals. Some were able to migrate to milder latitudes, while others were doomed to extinction. Even if winters were no harsher than today, the difference lay in the fact that summer no longer existed. The exact number of glaciations during this period is open to debate. 4 major glaciations have been clearly identified, separated by interglacial periods. These were the Gunns Glaciation from 760,000 to 530,000 years ago, the Mindell Glaciation from 650,000 to 350,000 years ago, the Risk Glaciation from 300,000 to 120,000 years ago, and the Worm Glaciation from 80,000 to 10,000 years ago. An important detail in the history of the Earth differentiates this ice age from the others. Man is now at the heart of the glaciations. In fact, it was thanks to these ice ages that the great human adventure began. Climate change means lower sea levels. Far from being a tragedy for mankind, this is actually a door opening for our ancestors from the African continent, Homo erectus, to travel north. In Europe, the cold sets in a little more each winter. Forests wither for lack of water. Oak forests give way to cold, arid steppes. The herds of animals that still roam the plains in search of moss and lichen are a godsend for the human tribes living in Europe. With their rudimentary tools, they catch the young animals and take the adult ones that have already died. As the years go by, the extreme cold sets in, with temperatures dropping to minus 30 degrees Celsius or minus 22 degrees Fahrenheit. Glaciers extend as far as Scotland and the northern Netherlands. The tribes of men, who may have ventured out before, return down in search of warmer lands and temperatures. At this time, fire still eluded them. Ice caps more than 3,000 meters or 10,000 feet thick cover Greenland, North America, and Siberia. All the water used to form these glaciers has caused sea levels to drop by 100 meters. new lands are revealed. The men who populate the African continent now have new prospects. Europe and its herds of reindeer were all the more attractive as the tropical forests had not withstood the heat, and savanna and desert now decorated the landscape. This glaciation lasted for around 80,000 years until an interglacial era began, with the climate warming for around 20,000 years. This cycle has been repeated 4 times to date. It has to be said that the most common state of our planet over the last few million years has been glaciation. In the midst of these glaciations, man has been able to adapt. He protected himself against the cold. Glaciations opened up passages in the sea, and man has continued to travel through glaciations and deglaciations. The event that forever changed its relationship with the climate was the domestication of fire, 400,000 years ago. From then on, it penetrated cold regions. They could now set up camp, build shelters and cabins. They can live on permanently frozen ground, their means of heating eternally at hand. After an ice age lasting over 90,000 years, the last great deglaciation began 21,500 years ago and lasted around 10,000 years. At the end of this period, the Earth underwent profound changes. Its average temperature rose by around 4 degrees. The gigantic ice caps that once covered a large part of the North, as far north as Belgium and Europe, melted. Sea levels rose by more than 100 meters. Flora was radically transformed, and the global water cycle intensified. Over 20,000 years ago, the Earth's climate was stable. Atmospheric CO2 levels were relatively low. It was cold, and the oceans were much lower than they are today. 19,000 years ago, a tiny area in the north began to warm up, while the south remained cold and hardly changed at all. CO2 is still low, and the ice caps are not moving. This evolution of the north is undoubtedly due to orbital changes that brought the Earth closer to the sun in summer, while the south was plunged into shadow. The continents are concentrated in the north at high latitudes. This is where the ice caps were formed. Even the slightest warming, of the order of a fraction of a degree, is enough to cause a large volume of ice to melt. Fresh water then flows into the Atlantic. The Atlantic is like an ocean corridor, linking the 2 poles. It carries warm water from the intertropical Atlantic far northwards. Once in the polar zone, this water loses its heat to the atmosphere. It becomes denser and sinks to the depths before flowing southwards. This circulation brings heat from the southern hemisphere to the northern hemisphere. However, if an influx of lighter fresh water occurs in the North Atlantic, the heat in the south may have accumulated as the north cooled. This phenomenon may explain why, 17,500 years ago, the situation shifted. Temperatures in the south rose and the north cooled. Atmospheric CO2 levels rise slowly. After 1,500 years, temperatures in the north also start to rise again, along with the amount of atmospheric CO2. This time, 16,000 years ago, warming affected all latitudes and zones. Atmospheric CO2 levels rose at a faster rate. According to scientific research, warming in the southern hemisphere caused massive degassing of the Southern Ocean, releasing massive amounts of carbon dioxide. By 10,000 years ago, warming had reached its definitive value. Atmospheric carbon dioxide levels stabilized. Over the next 4,000 years, the ice caps will retreat. This scenario could foreshadow the future of our planet if it is subjected to another episode of massive warming. In just 3 centuries, human activity has produced and released into the atmosphere 30% more carbon dioxide than during the last deglaciation, which lasted 10,000 years. For just over 10,000 years, the Earth has been in an interglacial period, characterized as a warm period known as the Holocene. Melting glaciers caused sea levels to rise to their present levels 6,000 years ago. It was at this time that the Black Sea began to fill up. The ice sheets gradually melted, and the land that had been hidden beneath them was freed from the ice and brought to the surface. Temperate fauna and flora reclaimed the middle and high latitudes. As for those that were adapted to the cold climate, they occupy other ecological niches. The rise in temperature during this interglacial period is not without consequences. In tropical zones, rainfall increases, leading to the shrinking of deserts. Rising sea levels isolate the British Isles from the European continent, moving habitable areas northwards. While flora and fauna have not changed significantly, the distribution of species has. Herds of large herbivores left the tropics as they became invaded by vast expanses of forest. They are now interested in the savannas that have appeared in the northern and southern deserts. In the northern hemisphere and Australia, megafauna are becoming less and less present. Large mammals are affected by a wave of extinction. The disappearance of mammoths and other large herbivores has had an impact on the climate. When these animals were present 12,000 years ago, they emitted 9.6 million tons of methane per year. As they disappeared, atmospheric methane levels fell, and so did the greenhouse effect, causing the planet to cool. The mammoth was a remarkable animal. Closely resembling today's elephants, it had a large head with a trunk, and a massive body with 4 pillared limbs. The largest species reached between 6 and 8 tons. Throughout their evolution, they adapted to ice ages and cold waves. The size of their ears and tails has diminished considerably. The hair, most exposed to thermal shock, could reach a meter in length. Their wool was 6 times thicker than a human hair. Their highly developed sinuses enabled them to process immense quantities of cold air. Their prominent tusks could reach up to 5 meters or 16 feet, an ideal tool for flushing out grass buried under the snow. Mammoths aren't the only ones affected by the extinction wave. In Australia, large species of reptiles and marsupials are disappearing. In North America, megafauna are not spared either. Mastodons, relatives of mammoths and elephants, are suddenly disappearing. The great land sloths, which grew to the size of cows, did not survive. In the family of large carnivores, the American cheetah, the saber-toothed tiger, and the American lion are no more. Giant armadillos, giant bears, and giant beavers have also disappeared. Man's favorite game, the herbivorous wood-eating mammals such as the antelope, are also disappearing from North America. This megafauna has a long lifespan, a low mortality rate, and a slow population increase. Few predators are capable of attacking their adult specimens. Nevertheless, megafauna are highly vulnerable to climate change. The arrival and spread of early man coincided with the beginning of the extinction wave. The mammoth is an animal that provides mankind with everything it needs. ivory for tools, bones for building huts, fur for covering up and protecting itself from the cold, meat as food, and even grease to keep the fire burning. Man has therefore not hesitated to overhunt this giant of history, contributing to its disappearance. But man and hunting were not the only factors behind the mammoth's disappearance. Mammoths were extremely well adapted to the cold. Global warming during the Holocene caused the evolution of grass and shrub-filled steppes into coniferous forests and tundra regions. Although herbivorous, the mammoth's dentition was probably not equipped to consume tree foliage. Some species, such as the woolly mammoth with its thick fur that kept it warm even in freezing climates, could have died out from hypothermia, while others, such as the bison, have adapted to climate change. The increase in temperature on Earth has not been sustainable for them. Here we are. How did the very first life appear on Earth? According to some of the experiments carried out over the last few decades, notably Miller's, life could have hatched in a primordial soup, in small hot pools close to volcanoes, for example. How did scientists arrive at this hypothesis? It all began in 1924 with the hypothesis of Russian biochemist Alexander Oparin, according to which the first living cell was born in a primordial soup. This soup is rich in carbon compounds synthesized in the atmosphere from methane. Stanley Lloyd Miller, an American biologist now considered the father of the chemistry of the origins of life on Earth, continued his research and explored the hypothesis of this primordial soup. He developed a mixture of methane, hydrogen, ammonia, and water, similar to what might have been found in a pond during the Archean period. In this way, he attempted to simulate the conditions that would have prevailed after the formation of the Earth's crust. Miller enclosed these gases in a balloon and subjected them to ultraviolet radiation, similar to that of the young sun, as well as to electrical discharges similar to those that might have occurred naturally, such as during thunderstorms. After a few days, the chemist noticed a dark deposit forming on the walls of the water-filled balloon. This balloon is a representation of the Earth's ocean. Analysis showed that the balloon contained not only formaldehyde and hydrocyanic acid, two molecules that play a key role in the synthesis of organic molecules of biological interest, but also small quantities of amino acids, notably glycine. Prebiotic chemistry could therefore have been at the origin of life on Earth. It was during the Archean, and perhaps even as early as the end of the Hadean, that bits of life, the very first cells, were able to hatch. All conditions were present in this primordial soup. Then, the nature and movement of the water undoubtedly favored the development of these bacteria in the four corners of the globe. Numerous variants of Miller's experiment have since emerged as knowledge of the atmosphere and geology during the Archean period has evolved. These have helped to underpin our knowledge of the first life cells. Other discoveries, this time from outside the Earth, have led to the realization that elements favoring the creation of cells may have come from the universe. At least that's what the study of the Murchison meteorite, which fell in Australia in 1969, has revealed. It contains over 70 different amino acids, 8 of which are used in the composition of proteins. Similar elements have also been found in micrometeorites found in Antarctic ice. This time, Analysis suggests that huge quantities of complex carbonaceous matter were delivered to our young Earth just over 4 billion years ago. Scientists have also discovered that the gases escaping from underwater hydrothermal springs contain hydrogen and CO2, generating long chains of carbon and hydrogen. These hydrothermal springs would therefore be synonymous with the source of life, since they constitute the first steps towards membrane synthesis. This discovery brings us to our second hypothesis, undoubtedly one of the most probable in the light of our current knowledge. Here again, it's very difficult to be absolutely certain about the origins of life, the course of evolution, and the processes that triggered the birth of the very first cells. The laws of physics, chemistry, and even biology cannot fully solve the mystery. I'd like to give you an outline of one of the theories put forward, which is certainly as close to reality as we can get, based on the various experiments carried out and the chemical laws we know today. The origin of the first cell would ultimately be a succession of interactions and reactions. If we accept the hypothesis of hydrothermal springs, here's what would have happened. Hydrothermal springs are hot water springs found at ocean ridges, at depths ranging from 500 to 5,000 meters, or about 1,600 and 1,650 feet. They are found where two tectonic plates diverge and magma fills the openings as it solidifies. The rock then cools and cracks. These hydrothermal springs form rocks. They are not smooth and totally hermetic. They are stirred up by hot water rising from the earth and cold water rushing in. The rocks have a spongy feel, even though they are very hard and solid. If you magnify part of this rock, you'll see that there are cavities of sorts. These are little cells. They make the rock permeable and are partly made up of iron sulfide. Iron sulfide is an essential element in our equation. It promotes and accelerates certain chemical reactions. As you'll see in a few minutes, life is ultimately a succession of chemical, physical, and biological reactions. Even if you can't really see it with the naked eye, elements such as ammonia, hydrogen, hydrogen sulfide, methane, and phosphorus compounds rise up from the depths of the earth. Within these permeable rocks, acidic seawater flows intersect and intermingle with alkaline freshwater flows. This mixture of seawater and freshwater, as well as elements brought up from the earth, will react when they come into contact with each other. Each cell stores these substances and preserves them at a high temperature. Don't forget that we're standing on the edge of a hydrothermal vent. Heat favors certain chemical reactions. This is the case here. The cells are like little test tubes. This high-temperature contact between 50 and 70 degrees Celsius, or 122 and 158 degrees Fahrenheit, leads to an initial chemical reaction that releases energy and produces new substances. And not just any substances. Sugar, amino acids, and even nucleic acid bases are born. In our rock test tubes, these new elements are bathed in a mixture of water and preserved at an ideal temperature. This allows them to continue their chemical marriage. After a series of successive reactions, the amino acids bind together to form short chains. These short chains, known as peptides, are one of the prerequisites for making proteins. We're slowly approaching the first living cell. As for sugar, It binds with phosphate and one of the elements present in nucleic acid to create what are known as nucleotides. Nucleotides are one of the building blocks of RNA, one of the building blocks of proteins. Another phenomenon is at work in the molecules in these rock cavities. At the same time, other chemical reactions produce DNA. DNA is more stable than RNA, making it easier to store genetic information, something that hasn't really been the case until now. These new molecules are still very primitive. They're a blueprint for more complex life. For the time being, they are still unable to move and remain trapped in their stone caves. Nevertheless, they are already capable of reproducing even beyond their rocky chamber. They can transmit their genetic information to the neighboring cavity and proliferate all along the rock. Precisely when, why, and how? We don't really know, but it turns out that these molecules are also capable of producing fats or lipids. These elements are hydrophobic and cling to the rock walls. Gradually, the lipids spread out over the wall, forming a kind of organic cell membrane. These new abilities are recorded in the DNA so that they can be reproduced. But they are still very fragile. New proteins have been grafted onto these membranes to promote and accelerate certain chemical reactions. They are now capable of producing a cell envelope. This makes them more robust and resistant. At this stage, there are two possibilities for these first molecules to become archaea or bacteria. The cells of these two life forms are then made up of a permeable envelope, enabling them to activate certain chemical processes. But they also have an outer wall, an outer envelope that protects them. Inside, they can produce more complex molecules and record them in their DNA. After a long and laborious chemical process, life can finally emerge. But isn't there a question on your mind? Do you remember that these archaea and bacteria are trapped in rock cavities? How did we come to have life in the four corners of the world and in every nook and cranny of our oceans? Locked in this way, they couldn't move around and expand their territory. Nothing is less certain, but it is assumed that the walls of the thermal vent rocks collapsed or cracked, perhaps after internal Earth activity, which would have released them. Their tough, permeable outer walls then play an essential role. They enable archaea and bacteria, once they have escaped from their protective incubator, to settle somewhere near the chimneys. A new rock, a crevice, a crack. They take up residence in a new place that offers them hospitality. Sterile and devoid of any living form, this new environment is then colonized by life. For these organisms, conquering new territories means adapting to new environments and evolving. It's the beginning of a new era in which biodiversity is in its infancy. Armed with this knowledge, you're ready to discover more about the evolution of life on Earth. Do you remember, before tackling the evolution of the very first bacteria, what led us to analyze the cavities of these hydrothermal vent rocks? It was the stromatolites. We were faced with a landscape completely different from what you can see through your living room window. Everything seemed uninhabited. The landscape before us was nothing but rock and water. I'd like to come back to the grayish rocks we encountered earlier. You need to take a closer look at these stromatolites. They're very special, you'll see. This kind of gelatin is actually half living, half rocky. I know, it's quite incredible and rather surprising. Gelatin is made up of bacterial filaments which trap carbon from the air and incorporate it in the form of sediment. This forms the rocky ball you see here. It's through this process that these half-living, half-rocky structures are formed, giving rise to stromatolites. Some of these were discovered 3.5 billion years ago while drilling the Craton in Western Australia. A craton in geology is a continental area corresponding to a formerly consolidated zone of the lithosphere. Other, even older stromatolites have been discovered, this time in Greenland. These small geological structures are thought to have resulted from the activity of colonies of aquatic bacteria. Their activity promotes the precipitation of fine films of limestone on the seabed. Over time, these films are superimposed, producing the pointed cone-shaped structures and crushed bumps known as stromatolites. These date back 3.7 billion years. From then on, and for more than 1.5 billion years, life on Earth was exclusively bacterial. The Proterozoic is the third and final period of the Precambrian. It spans almost 2 billion years, from 2.5 billion years ago to 542 million years ago. This eon is divided into three periods. The Paleoproterozoic, from the Greek paleos, meaning ancient, stretches from 2.5 to 1.6 billion years ago. Mesoproterozoic, from the Greek mesos, meaning middle, from 1.6 to 1 billion years ago. Neoproterozoic, from the Greek neos, meaning new, extends from 1 billion years to 542 million years ago. Let's go back to where it all began, at the beginning of the first period that makes up the Proterozoic, the Paleoproterozoic. Here we are, the Paleoproterozoic. There's something that must seem very strange to you right now: the orange atmosphere. According to research carried out by an English university team on marine sediments in southern Africa, 2.5 billion years ago, the atmosphere was unbreathable and orange. This methane fog is undoubtedly partly to blame. Earth looks like Saturn's moon Titan. The temperature at that time was freezing. Between 2.5 and 2 billion years ago, the Earth underwent a major period of glaciation. A few hundred million years later, it would experience others. You're probably cold just looking at these images. It has to be said that temperatures during this period were far from mild. Surface temperatures averaged minus 25 degrees Celsius or minus 13 degrees Fahrenheit. But minus 50 degrees Celsius or minus 58 degrees Fahrenheit are not uncommon in the region. The Siderean, the first period of the Paleoproterozoic, and part of the following period, the Rhyatian, saw one of the most severe ice ages the Earth has ever known. This glaciation, known as the Huronian glaciation, took place between 2.4 billion and 2.1 billion years ago. It was one of the most important glaciations, but also one of the longest, 300 million years. There are currently two hypotheses still under debate as to the cause that led to this glaciation of the Earth. The first involves a reaction between oxygen and methane. This phenomenon, known as Great Oxidation, transformed methane into carbon dioxide by reacting with methane. This mass-produced carbon dioxide would have produced a greenhouse effect 30 times smaller. Another hypothesis is that volcanoes were dormant for almost 250 million years. With much less carbon dioxide present, the greenhouse effect would have been correspondingly reduced. The Huronian glaciation is not the only natural phenomenon to have marked the Silurian period. At this time, we also speak of banded iron formations, a rather convoluted term to define the birth of iron deposits of a different kind, made possible by the presence of oxygen. Oxygen is present everywhere in the stratigraphic layers of this period. The origin of its presence is undoubtedly the proliferation of blue-green algae. Yes, since our visit to the Archean, things have changed a little in terms of flora and fauna. Bacteria have grown and expanded their territory. The sugar from which they derive their energy has been drastically reduced. The symbiosis they used and the photochemistry that enabled them to survive are no longer possible. So they had to adapt to their new environment and adopt a new way of life using solar energy, photosynthesis, as plants do. This is undoubtedly what led to their confusion and earned them the name of blue-green algae. Until now, our primitive cells drew their energy from chemical substances. These substances are found in abundance, straight from the bowels of the earth. It's sugar, produced through various chemical reactions, but for a variety of reasons this sugar will one day run out. Bacteria will have to adapt if they are to survive, and that's exactly what they do. They manage to draw their energy not from sugar, but from the sun. They use a new mode of operation, photosynthesis. Specific bacterial cells capture the sun's rays. Thanks to this accumulated energy, they are able to break down water into hydrogen and oxygen. This action releases carbon dioxide. The oxygen is released, while the hydrogen and carbon dioxide produce carbohydrates. And these carbohydrates are rich in energy. They're what keep bacteria alive. These photosynthetic cyanobacteria are unicellular, prokaryotic organisms, i.e., their cell structure does not include a nucleus. By using the sun as an energy source to synthesize organic matter, they release oxygen. Lots and lots of oxygen. The first oxygen molecules triggered a series of reactions, bringing about new changes for our planet. Initially, the production of oxygen was offset by the production of iron oxide, and probably had no real impact. But the process soon reached saturation point. There was no longer any reaction to stop the release of oxygen molecules into the air. If the Amazon is the green lung of our planet, the ocean is the blue lung, and the very essence of the air we breathe. It is from the ocean that we still derive much of the oxygen we breathe today. The presence of oxygen in the atmosphere encouraged new transformations in the first living organisms. Hitherto prokaryotic, eukaryotic organisms with well-defined nuclei are now emerging. Genetics adapts to new environmental conditions. Look, here are two algae, two new organisms that symbolize the first steps of evolution. The first is a green algae, of the chlorophytus class. The second is a red algae, of the rhodophytus class. Both use photosynthesis to synthesize organic matter. These multicellular organisms also contribute to the expulsion of oxygen into the atmosphere. But they're far from the only ones to populate the ocean. Many other species have made a place for themselves. Here we find another multicellular eukaryote, quite similar to algae, the Grypania spiralis. It's thread-like and twists itself, a bit like a whirlpool. And here's Eosphera. We've learned a lot about this spheroidal organism. From the first elements we were able to analyze, it appears that it reproduces by fission. Each new cell remains attached to the mother cell, forming a mucilaginous sheath. During the same period, we also find a type of plankton that also uses photosynthesis to survive: phytoplankton. We could stop here on the presentation of paleoprotozoic animals. Until a few years ago, it was thought that only single-celled organisms populated the world. But in 2010, a university team from Poitiers, France, discovered nearly 250 fossils in Gabon, near Franceville. And, incredible as it may seem, they date back 2.1 billion years. We could never have thought that multicellular organisms could have colonized the planet so many years ago. The oldest, those of the Ediacaran fauna, which we'll talk about later, date back some 600 million years. Before the discovery of Franceville, these fossils were the oldest known traces of living organisms. Here we have representations of these complex multicellular organisms with soft, gelatinous bodies. They are neither quite animals nor quite plants. In the end, we know very little about these organisms, apart from their great variety of forms. You can see lobed organisms with serrated edges, smooth-edged organisms, slender, elongated organisms, discoid organisms, or even some with an accumulation of small rounded subunits. Over the years, the animals we've met have left traces in the sediment, but their soft bodies don't fossilize. That's why it's so difficult for us to get a realistic view of these organisms. All unclassified microfossils are classified as acritarchs. The majority are probably algae of all shapes and sizes. Although they differ in appearance, they all have one thing in common: oxygen production. For many bacteria, the increase in oxygen in the atmosphere represents unprecedented chaos. But this catastrophe, while bringing them to a tragic end, also fosters the expansion of other life forms, eukaryotes. When we speak of a unified Earth and a supercontinent, we usually mean Pangea. But the continents have only linked and unlinked over billions of years. Pangea was not the first supercontinent to form. At the very beginning of the Mesoproterozoic, a supercontinent called Columbia began to break up. Over time, the supercontinent Rodinia was formed. This was a period of great geological and geographical upheaval, but it was also marked by the appearance of the first modern eukaryotes and sexual reproduction. Let's take a look at one of these specimens. Meet Bangiamorpho pubescens, a red algae. It's one of the oldest complex multicellular organisms known today. So far, we've talked a lot about how these organisms derive their energy, or about their many and varied forms. But during the Mesoproterozoic era, 1.2 billion years ago to be precise, an incredible event occurred that turned evolution on its head. Bangiamorpha pubescens was part of this revolution in life on Earth. Extensive analysis of these fossils has demonstrated the presence of differential spore and gamete formation. This means that the red algae is sexual. This new mode of reproduction not only favors genetic recombination, but also, and above all, complex multicellularity. This is one of the essential building blocks in the evolution of life on Earth. Cells join and attach to each other. This was not the only radical change to take place during this period. Parallel to this event, another revolution in the world of living beings is underway. Cells pass a new milestone. According to scientists, a genetic accident also occurred just over 1 billion years ago. When we think of a genetic accident, it's easy to think of rather dramatic consequences. But genetic accidents can also bring unexpected benefits. To understand this, we first need to know what a genetic accident is. When a cell divides to duplicate itself, it reproduces its DNA exactly. Indeed, this is how it happens in the vast majority of cases. However, it also happens that a change, sometimes minute, occurs during DNA copying. This is known as a mutation. A mutation can be fatal for an organism. It doesn't have the right codes, its functioning is disrupted, and it can't survive. But a mutation can also give rise to new abilities, unexpected and beneficial abilities. Such was the case with the genetic accident that occurred 1 billion years ago. Initially, our little unicellular bacterial organisms were equipped with a flagellum, a sort of little tail. They have a particular DNA with a specific code, notably for proteins. During duplication, the DNA has mutated. A genetic accident modified the original code of this unicellular being, giving the proteins new capacities. They can now interact with others. This phenomenon is crucial to the evolution of life and the diversity of living organisms. It is thanks to this key stage that we pass from a unicellular organism to a multicellular organism. These multicellular organisms become increasingly complex and different from one another. This is the possible birth of plants, fungi, and even animals. For the time being, jellyfish, sponges, corals, polyps, and anemones are gradually taking root at the heart of our underwater world. It's time for us to meet a handful of them in the next period. See you in the Neoproterozoic! We've reached the very last era of the Precambrian. It prepares the Earth for enormous upheavals in the living world. It heralds the imminent arrival of the Cambrian and the explosion of life on Earth. This era takes place between 1 billion and 542 million years ago. It was marked by the fragmentation of the supercontinent Rodinia. Around 800 million years ago, the Earth's landscape, as seen from the sky, was totally different from today. The Earth was a vast ocean from which a single land emerged, Rodinia. 50 million years later, the continent is gradually breaking up. Plate tectonics played its part. The continent began to fracture into 2 parts, giving rise to the Panthalassa Ocean. This slow division continued over the following millions of years. Like a jigsaw puzzle, it fragmented into several pieces. According to the most recent studies on the subject, it seems that the supercontinent Rodinia broke up into 8 distinct parts. As you'll see, this intense terrestrial activity is both an unprecedented shock and a veritable springboard for life to develop to its full potential. Under the effect of hotspots, the continent of Rodinia is pierced by magma spears. They cut through the Earth's crust, spewing out huge quantities of lava. The ground then began to fracture. This event was accompanied by the opening of oceans and inlets, which increased the amount of water vapor in the atmosphere, and hence rainfall. The carbon present in the rain, in the form of carbon dioxide, soon found its way back into the ocean, trapped in sediments in the form of carbonates. At the same time, the enormous lava flows produced by the Rodinia fracture formed basaltic surfaces on the surface of the continents. When eroded by moisture, these basaltic surfaces consume 8 times more carbon than the same granitic surface. Over thousands of years, atmospheric CO2, a greenhouse gas, decreases drastically. As a result, the Earth enters a new period of extreme cold. In fact, our planet has undergone not one, but 2 periods of glaciation during this period. The first took place 760 million years ago, the second 150 million years later. The latter was one of the most intense. The first stretched from 760 million to 700 million years ago. Then, shortly afterwards, between 620 and 590 million years ago, the Earth faced a second, full-blown ice age. The warming between the interglacial periods was due to volcanism, which was very active during this period of supercontinent fragmentation, releasing large quantities of CO2 over millions of years, triggering a greenhouse effect large enough to thaw the Earth. Bits of life seem to have found refuge to survive this difficult period. Between these 2 ice ages, the first 2-sided animals appeared. Worms that resembled annelids, others priapulids. Then ice, snow, and cold returned. Our planet was nicknamed Snowball Earth. Seen from space, you probably wouldn't recognize our blue planet. Covered in ice and snow, the pack ice extended, according to studies, perhaps as far as the equator. While this line is synonymous with humid heat, dense, lush forests, incredible waterfalls, and an extraordinarily rich fauna at that time, the equator line would have been almost frozen in ice. All hope of life seemed to be extinguished. No organism could survive here. And yet, it may be that some of them did. How can we be sure? This time, it's not the remains, but technology that's giving us a little help in discovering more about our history and this complex period. Computer simulations, based on advanced calculations and complex algorithms, show the existence of refuge zones running along the equatorial line. For millions of years, organisms lived in isolation in these shelters, then, with the thaw, managed to expand their territory and adapt to a wider environment. Rock analyses show a significant reduction in carbon levels and thus in organic activity. Photosynthesis was also cut off over millions of years. Bacteria therefore suffered the full force of this glacial chaos. The ice cap could be heard hundreds of meters below the surface. At times, temperatures dropped as low as -50 degrees Celsius or -58 degrees Fahrenheit. Many bacteria did not survive, and the first algae probably also lost a significant number of specimens during this period of extreme cold. One might think that this glaciation dealt a fatal blow to the evolution and expansion of life on Earth, but it would be a mistake to stop at this preconceived idea. Life is an eternal adaptation. That's what evolution is all about. Look at this little organism. It's a trichoplax. At first glance, it doesn't look like a highly evolved creature. Barely visible to the naked eye, it looks like a large amoeba. It's a placozoan. It belongs to the group of organisms known as metazoans. Placozoans are ultimately metazoans with a particularly simple structure. Trichoplax has no head, tail, legs, or nervous system. It has no digestive tract, nor does it have extracellular digestion. One wonders how it can survive and qualify as a living organism. Yet it has a body covered with cilia, which it uses to move around. Its shape is rather unusual, and we know very little about it. But if we delve a little deeper, we might find that Trichoplax has only 4 different cell types. This confirms its place among simple organisms. And yet, this little animal, along with others of its kind, has undoubtedly played an extremely important role in evolution. This little body contains the protein genes that enable the anteroposterior, dorsoventral axes, and even 4 of the visual pigment genes. Imagine such a simple, primitive animal is one of the keys to the evolution of living things. It's not alone in this environment, since after the ice ages, algae developed extensively and spread throughout the world's oceans. Underwater waters are becoming more vegetated. Contrary to appearances, this climatic catastrophe was a godsend. It led to a major diversification of living organisms. When the thaw starts, a whole series of chain reactions ensues. The erosion of continents as the ice melts is said to be responsible for the release of vast quantities of nutrients. This abundance of nutrients encourages the expansion and proliferation of phytoplankton. As a domino effect, or snowball effect in our case, the presence of phytoplankton has encouraged the release of oxygen into the atmosphere. This element is one of the keys to the emergence of multicellular life. It exploded in the Cambrian. But for this explosion of life to take place within a few 100 million years, there is still a long way to go in the Proterozoic. Let's explore the oceans to discover the many organisms of this period. The big problem we've had so far is that organisms were made up of soft bodies. After so many years, time has taken its toll on the traces and vestiges of the past. But by the end of the Proterozoic, fossil remains were making it possible to learn more about the flora and fauna of this pivotal period in biological evolution, thanks in particular to the discovery of the Ediacaran fauna. Around 600 to 700 million years ago, organic evolution took a new turn. Cells are now divided into 2 layers. The first is the layer of inner cells, known as the endoderm. This is covered by an outer cell layer, known as the ectoderm. These new beings with 2 embryonic cell layers are known as diploblastic organisms. This term designates animals without mesoderm, with only an outer wall, a digestive wall and organs derive from these walls. These new abilities have enabled very different animals to appear on Earth. These include the sponge family, as well as cnidarians such as jellyfish, coral, and hydra. For the first few billion years, life was only possible in an aquatic environment. Although we are fully aware of this ancient life, we can only perceive minute traces of it today. What's more, these organisms have evolved very little so far. Perhaps some chemical evolution has taken place, but again, this is impossible to determine today. The remains of the past are too vague, too abstract, to draw any real conclusions. Scientists have great difficulty differentiating between certain remains. Are they the remains of bacteria or algae? Only size can sometimes distinguish between the two. But from now on, everything changes and everything becomes possible. Earth will never again be uninhabited. Evolution is underway. Life takes on a new lease of life. Although organisms always consist of a soft body, they also have integuments, i.e. a set of external structures. an integumentary system, which protects the animal from the outside environment. Today's animals have a variety of integuments, including hair, scales, and feathers. This integumentary system is a real game changer for scientists, who can now rely on much more convincing evidence. Teguments are resistant and have enabled fossilization. Here's what these remnants of another time have revealed. The first thing we notice is that organisms begin by gaining a few centimeters. For billions of years, they remain microscopic. From now on, they'll be bigger and bigger. The rangiomorph is one of them. It's an organism that resembles a long leaf. It also has a stem connected to the seabed. Scientists have put forward a hypothesis about this evolution. They wondered why organisms grew taller. The first theory was linked to feeding, but was soon abandoned. There were plenty of nutrients around, so it's highly unlikely that this criterion had such a significant impact on evolution. If not to feed more easily, why grow? The number of small specimens grouped alongside this large rangiomorph suggests that larger size may have favored reproduction. The animals also developed a new shape. They are symmetrical animals with appendages that function in pairs. This particular shape enabled them to become burrowing animals. They feed on organic matter covering the ground. They can be tube-shaped, leaf-shaped, or sac-like. The main representative of these late Proterozoic animals are grouped together in what is known as the Ediacaran fauna. It has been so named since the discovery, in 1946, of a wide variety of fossils around 560 million years old in Australia's Ediacaran Hills. Since then, similar specimens have been found elsewhere in the world, including Canada, South Africa, Siberia, and Europe. Here are a few animals from the Ediacaran fauna. Here, these circular animals with concentric rings are Aspidella. They measure up to 8 centimeters or 3 inches long, and 4 centimeters or 2 inches wide. A little further on, it's a Charnia. There are 3 known species of Charnia: Charnia wardi, Charnia antecedens, and Charnia masoni. The latter looks a little like a feather or leaf. The Charnia wardi genus was one of the largest, growing up to 2 meters or 7 feet. Other species resemble animals we know today: jellyfish. The jellyfish group was quite common in the oceans at the time. Cyclomedusa davidi and Cyclomedusa radiata are among them. Another animal, another form. Here's a Sphrygina. It too bears some resemblance to the fauna we know. It resembles a worm with a head, a body, and a kind of spike that allows it to anchor itself in the seabed. It probably slid through the mud to find nutrients. Seaweed is also ever present. Here again, we have a lovely specimen of Bangiomorpha pubescens right in front of us, a red algae. Finally, a Dickinsonia. We know very little about it, and scientists are still finding it hard to classify. However, we do know that it was able to move, as traces of movement are attached to it. Oval in shape and measuring from a few millimeters to around 1.4 meters or 5 feet in length, it has a radiate structure. The term radiata is also used to define this criterion. This means that these organisms, invertebrates, have axial symmetry with cyclic patterns around this axis. Like most organisms in this category, Dickinsonia is also characterized by the 2 cell sheets we mentioned for diploblastic animals. That is, it has an endoderm and an ectoderm. These two layers are separated by an acellular gel. There's another rather unusual feature of this animal. A single orifice serves as both mouth and anus. This is the very beginning of evolution, and differentiated organs are not yet in vogue. Summing up the main stages of biological evolution in a few lines, it all really began 3.9 billion years ago. It's possible that this event occurred earlier, but there are no remains to confirm this. At that time, the largest living creatures were only 1/10 of a millimeter in size and were limited to the kingdom of bacteria. Nearly 1 billion years later, around 2.8 billion years ago, the cellular world evolved, leaving a small space for eukaryotes, organisms with a nucleus. They are capable of symbiosis with proteobacteria. They draw their energy from substances supplied by the Earth. A few 100 million years later, around 2.1 billion years ago, a new type of eukaryote appeared, more complex and elaborate. This time, these cyanobacteria took advantage of photosynthesis and drew their energy from the sun. By the end of the Proterozoic, more varied forms of organisms had become part of the cycle of life. They were able to move, were sexually mature, and diploblastic. Underwater riches are flourishing. Yet 542 million years ago, all these organisms disappeared. We don't know what caused this mass extinction. No meteorite, no volcano, no major glaciation was responsible for the disappearance of all the primitive forms of the Precambrian. But it is sometimes in the midst of chaos that positive things can happen. Remember, glaciation allowed eukaryotes to evolve. This widespread extinction, in turn, gave way to the Cambrian Explosion. This is one of the greatest stages in biological evolution. It makes a new turning point for the living world and for our planet. Most of today's major metazoan phyla will emerge. It's a veritable zoological Big Bang. Animal, plant, and bacterial species are about to emerge. The only thing that Precambrian and Cambrian species have in common is that they too will be born in the ocean.